Hello everyone, this is Brony Calc, and I'm here to talk to you about numerical bases. Now, some of you might be thinking that's a really boring middle school topic. You've seen all that you can get from it, and you really don't get why I'm making this video. Well, sure, the basic problem of let's add 110 base 5 plus 101 base 5. This problem has been done to, problems like this have been done to death. Convert to base 10, convert to base 9, yada yada yada. But there's a special set of problems where you don't even know you're working with bases until you've gotten pretty far into your method of attack. And these problems can show up in high school competitions and actually have relatively recently. So, let's get started with an older one from the 2007 ARML team round, number 4. We have a list of positive integers that do not contain the number 0. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9. Can't use 10, so we go to 11, 12, 13. We're going to keep going. And we need to find the 2007th integer on this list. Well, that doesn't really tell us much. All we know is it skips one of the digits. If it skips one of the digits, that means we have 9 digits to work with instead of 10. So maybe this is secretly a base 9 problem. But 9s don't show up, so let's try to get rid of that. We can't just subtract them. There are two ways to do this. We can either bump up all 9s to make them 10s, or really just 9s in base 9, so it'll look like this. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13. And that works. Then if we do it this way, we're just looking for your 2007, we're going to convert to base 9. And then if there's a 0, we'll just subtract stuff until it turns into 9s. Or, alternatively, we could subtract 1 from every number. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. It's the same sequence, except just shifted back a little. And we don't have to worry about messing with 9s, because when we do this, we're just going to add 1 to get the original, so the 9s will automatically show up. But now, if we do this, we're not looking for 2007 anymore, because we're starting with 0 instead of 1. We're looking for 2006 in base 9. Let's try it this way. We can try it the other way. I leave that to do on your own. It's actually rather fun, but can get a little messier if you're not careful. So, we have 9, its multiples, 981, 729. Those are the ones we care about, and of course, 1. So, first off, we look at this. 3 times 729 is in 2100, so that's too big, but 2 times 729, 1400s, that is smaller than 2006, so our first digit is going to be 2, representing 2 times 729, or 1458. You subtract from the original, and you get 558, I believe. 548, excuse me. So, 548, we want to subtract 8s. So, 8 times 7, 56, so 7 times 81 is bigger than this. But 6 times 81, which starts with 48, 486, that's going to be just the right size. So we have 2, 6. And now we just look at this. This we subtract. So we got 54 minus 48, that's 6. 8 minus 6 is 2, 62. So we're 1 less than 63. 63 would have been in 7-0, so we go 1 back to 6-8. Remember, there are no 9s. So we got 2-6-6-8. So our answer should be one more than that, or 2-6-6-9. Okay, so far so good, but that's just one problem, and it's 10 years old at this point. How about one that came out just this year from the HMMT February tournament, the Algebra and Number Theory number 1. So we have a polynomial q of x, and all of its coefficients are integers, and they are greater than or equal to 0 but less than 3. So there's 0, 1, or 2. And we don't really know what the degree is or what each coefficient is, but we have to find that out. What we are given is that q of the square root of 3 is equal to 20 plus 17 root 3. Yuck, yuck, 2017. So, we want to find q of 2 based on this. So we want to take this, use it to find the coefficients, and then convert that back. Well, let's start looking at what q of root 3 will look like. So we've got q of root 3 is equal to a0 plus root 3 a1 plus 3a2 plus root 3 3a3, just making the radical small, plus 3 squared a4 plus root 3 squared a5, so on and so forth. So at this point you should notice 3 to the 0 and 3 to the 0 times root 3. So we got 3 to the 0 times something plus 3 to the 1 times something plus 3 squared times something, so on and so forth. And those somethings are all 0, 1, or 2. So this is just expand notation in base 3. And since we know that each one of these separate ones, this is going to add up to an integer, and this will add up to an integer times root 3, we can break up our answer, 20 plus 17 root 3, into 2 parts. 20, which we need to convert to base 3 now. 2 times 9 is 18, so 202 is going to be our main polynomial. Is going to be our integers, excuse me. And then we have 17, which is just less than 200, so it would be 122. And so now we know what our coefficients are. We have 1 times 3 squared times root 3. So this is root 3 to the 5th, plus 2 times 3 squared, root 3 to the 4th, 2, 0, 2, 2. So now instead of root 3, we need to use 2's. So we have 2. 2 times 2 is 4. 0 times 4 is 0. 2 times 8 is 16. 2 times 16 is 32, and 1 times 32 is 32. So these add up to 64, or 16 and 4 add up to 20, and this adds up to 2, so 86. So, also not too hard a problem, but this video wasn't about showing you the hardest problems. Honestly, I can't solve the quote-unquote hardest problems out there. It was just to help you guys remember that sometimes the base notation you learn for those select few math counts problems can really come in handy in your high school competitions. So, if you liked the video, please leave a like, leave a comment, especially if you have any constructive criticism. I always appreciate it. And maybe check out some more of my videos, and if you like those, subscribe. I will see you guys next time.